Hello and welcome to JavaScript Marathon, a full week of free online courses in some of the latest leading web development technologies and concepts. Excited to introduce you to James Snell. Today he will be presenting advanced node training. A bit about who we are at This Dot. We provide architectural guidance, staff augmentation, on-demand subject matter experts, temporary CTOs, one-on-one pairing, mentorship, and open source strategy. If you're interested in seeing some of the work we've done with our amazing clients, take a look at our portfolio page at thisdot.co/portfolio. We are still hiring. If you're a senior software engineer, please feel free to send us your info at jobs@thisdot.co. Also, we have our full job listing at thisdot.co/jobs. Some amazing upcoming events. Since we are here for advanced Node training, we have a really great opportunity to dive into more Node. State of Node is on May 24th. And then Vue Contributor Day with Evan Yu and Simone Como will be on May 25th. And with that, I will hand it over to James.
Hello, everybody, and welcome to this JavaScript Marathon. Today, we have a very special guest, James Snell. You can follow him on Twitter at jsnell, Snell. I don't know. How do you say it?
J.A. Snell. Yeah.
J.A. Snell. Okay. And today we're going to do a deep dive into NodeJS. So this is going to be really amazing. And feel free to ask questions as we go and everything. But James, we're super excited about this. And yeah, feel free to get started.
Fantastic. Thank you, Tracy.
Mm-hmm.
All right. Happy to be here. Just a couple notes. I'm going to be just handwriting this. I don't have slides and I'm not going to show code. What I basically want to do here is take the time that we have to kind of go in deep on how Node works internally. It's for many years now, I've been helping a lot of folks out with performance issues with Node or debugging memory issues and those kinds of things. And in every single case, we've found that just giving people a better understanding of how Node is working internally and how it does things is the key to really making those improvements to performance and memory usage and those kinds of things. And there's a lot of little details in the implementation of these core Node APIs that a lot of people just don't realize. Because they're not thinking about it, that's where they kind of fall into little traps with performance. So we're going to cover a number of things. We're going to talk about some of the event loop basics, just kind of how it's working under the covers, and a few of the key details there that you need to know from a performance point of view. We're going to talk about Event Emitter, how that works. It's one of the earliest and kind of one of the most critical APIs in Node today. It's used everywhere. Pretty much everything is an event emitter. And we're going to deep dive into streams, both the Node streams and the web streams. By web streams, I mean like the WhatWG readable stream, the same API that you would have in a browser, now exists in Node. And I kind of want to talk through some of the differences between those models. And then I want to get into promises. Now, we only have about an hour and a half. There's a lot of information. We may not get through everything, so we're going to go as far as we can and go from there. If you have questions, just drop them into the chat. All right. So on the event loop, I'm sure you've all heard Node has this event loop, and you had this idea that JavaScript is single-threaded. So when the Node process starts, all right, so the box will be the Node process. We do have multiple threads that are started. You have the main process thread. Okay, so this is going to be, we'll call this main thread. All right, can everybody see the handwriting? Oh, okay, should be coming through. No problem. Great.
Yeah, looks
good. All right. So then we also have libuv sitting in here. And what libuv will do is it spins up a pool of threads. Now, by default, there are 4 worker threads in the libuv pool. All right. Those worker threads, those are responsible for going off and doing the IO, reading file from a disk, or in some cases doing some encryption, or in another case, reading from a socket, that kind of thing. That that's all handled by those libuv worker threads. Now on the main thread, we have the event loop, which is spun up. So it just sit there, it's essentially just a fancy for loop, right? And every time it iterates back around, we have a series of steps, things that it checks off. It'll check to see, okay, are there any timers that need to be, that have expired that need to be fired? Do we have any pending IO? So if you've asked one of these worker threads to go off and read a file, right? Is a chunk of that file available now to process? So all it does on every iteration of the loop is go off and check each of these steps. And I'm not going to go through all those phases right now. We don't have, it's just too much detail to go into right now. But at each one of those steps, there's a couple of things that happen. One, it'll check down in the operating system or whatever, did something happen that I need to pay attention to, right? And if there is, then it will invoke a callback. Okay. Now that callback, this C++, this event loop in the main thread, all of this is happening at the C++ level, right? So we haven't touched any JavaScript yet. Okay. This is just a for loop happening at the C++ level. It'll hit a C++, a native callback, and that callback will decide what what needs to happen. Sometimes we handle those entirely at the native level of Node, right? So there's no JavaScript is invoked at all. But most of the time, like in the case of a timer, or if you've scheduled some file to be read or whatever, there is a bit of JavaScript that gets to be that is called when it hits that event. All right. So we're going to have a series of tasks, and we're going to represent these just by these little boxes here, and they get invoked. So the event loop turns, it hits these steps and says, okay, I have to do something. It's important to understand that while it is in each of these boxes, while the event loop is running one of these steps, the event loop stops, right? The execution of that loop is blocked until that step completes, okay? So it'll go through, there might be, on one loop, there may be nothing for it to do. On another iteration of the loop, there might be 1,000 things for it to do, right? The event loop will not be turning while each of those individual things is happening. So if it's executing some bit of native code, if it's executing some bit of JavaScript, that means the event loop cannot turn to do something else, which means any file IO is blocked. Any network IO is blocked. Timers will be blocked. It won't be able to turn over until that step completes, right? Now that's critical to understand, because if one of these blocks is executing your JavaScript code, if your JavaScript code is doing a whole bunch of synchronous stuff, right? That event loop is not turning. File IO is not happening, right? All these, these asynchronous tasks that you may have scheduled, those aren't actually getting completed while that JavaScript is running. That's the only thing that's happening, right? Now, any tasks that you have over here in this libbv queue, I mean, those things are still happening in parallel, but the event loop can't get around to doing anything else until your JavaScript is done running, right? That concept, I've actually had people argue with me that, oh no, if I throw it in a new promise, that just means it's executing in parallel. I had one customer actually tried to argue that creating a new promise in JavaScript was just like creating a new thread in Java. And it's like, no, I had to, back that up and kind of explain, how this event loop worked, that there's really no such thing as asynchronous JavaScript, right? JavaScript is synchronous, it's blocking, it runs, right? Where you get the asynchronous aspect of it is by having it run in smaller chunks and using scheduling mechanisms to say, okay, I'm going to defer running this function until later, until after this other set of events happen. All right. Critical to understand that aspect of the event loop. Now, what happens when we do hit the step? So we're going to draw the event loop again. We're going to hit a step here that and again, this is a C++ callback, and it needs to invoke some JavaScript. So what happens? It's going to we use V8 here. So we're going to use some V8 APIs to actually go off and execute a JavaScript function. Okay. That's, the user code, that's node code, wherever that JavaScript came from, doesn't matter. We're going to go off and execute that. And again, that is a completely synchronous call, right? Over here on the side, within Node, we have two queues. I'm going to simplify it and just say there's a queue here. But we call this the next tick queue. Okay, it's a horrible name for it because it doesn't, it has nothing to do with actual ticks of the event loop or whatever else. But it's this queue that sits over on the side. Whenever we call up to JavaScript and we execute that function, there is a API in Node called process.nextTick. Okay, and the argument to that function or to that API is a function. Okay, what process nextTick does is it just appends that function argument to this queue that sits over on the side. That's all it does. When control returns, when the stack unwinds after this JavaScript bit of JavaScript right here is run, and control returns back to the C++ layer, Node goes out and drains that queue by synchronously, in the order that they were added, running each of those functions that were passed into it. Okay, so it goes off that we have the native callback. It runs some JavaScript. JavaScript might schedule these next ticks. Control returns, right? When it returns, it'll go back in and say, okay, here's another function. I'm going to drain this queue, and it'll drain it to completion before it can move on to the next step in the event loop. Okay, which might do the exact same thing, right? So you just have, as the event loop's turning, you just have these. Okay, I'm going to execute some JavaScript. I'm going to execute a little bit more JavaScript. Move on the next task. Execute some JavaScript. Might have a few more things to do. Okay. Now, what ends up happening? The comment is it's like request animation frame. It's very, very, very similar. What ends up happening here for a lot of people when they get into some performance issues with Node is they don't understand that whatever bit of JavaScript they're running, it's stopping everything else. Again, I keep reiterating this point, but it's one of the most critical pieces here. While your JavaScript is running, you can't respond to your IO. I had one customer in particular. This was a number of years ago. They had a Node server that was running GraphQL. They were using the Apollo server. Their GraphQL queries were very, very complex. And when they would get one query in, it would actually send queries like 10 to 15 backend services, right? Get all that data back, coalesce the response into a single response back to the client. What they, I think they ended up having something like 4 requests per second on the server, and they're like, "What the heck? I mean, this is ridiculous. Why is it so slow?" What was happening is that the request processing in Apollo was so slow at that time. There was so much synchronous processing that was happening. Those backend requests to the backend servers, those were happening, and those backend services were responding back to the Node server. But the event loop was being blocked for so long by doing all that synchronous processing that the event loop would not get back to processing the returned data until the timeouts would fire. And suddenly all of the requests, a lot of the requests were just failing with timeouts and all kinds of different errors. And it's because they were blocking that event loop. All of the backend IO happening just fine. The backend services had no latency on response. They were chugging along nicely. But just processing the GraphQL, it came down to processing the GraphQL AST, that parsed tree for the query, was so complex. Whenever they would get a whole bunch of queries in all at once, it would just bring the event loop to its knees and would not allow it to proceed. So, understanding anytime you have JavaScript running, nothing else is happening. Okay, just that JavaScript. That's the only thing that Node, for all practical purposes, that's the only thing that's happening. Right. So the key trick to Node performance: keep your JavaScript functions small. Don't block. Right. Keep them, have them go very, very quickly, and use the scheduling mechanisms to defer work. When I say scheduling mechanisms, I mean things like Xtick. There's another one called Queue Microtask. Okay. Now the difference between these, they're 2 separate queues, but they're invoked one after the other. Okay. What NextTick, this is the original one from Node. Okay, this is again drained as soon as that stack unwinds from JavaScript back to C++. The Queue Microtask is actually this is the thing that processes promise continuations. So thens, catches, and finallys in V8. Node will drain this immediately after it drains the next tick queue. So every single time we return from JavaScript back to C++, we go up, we say, are there any next ticks? Yep. Execute all those functions. Then we say, okay, are there any promise continuations? So if any promise has been resolved or rejected. If so, all of those will be drained immediately at this point too. So this can happen thousands or tens of thousands of times per event loop turn. It depends on how many promises you have, how many next ticks you've scheduled, right? I had one customer that in one turn of the event loop, they were creating and synchronously resolving about 30,000 promises every single turn, right? And every single one of those ended up with a function added to the queue microtask. So this can happen massive amounts of times, right? And these are all things that people don't think about, like what is the structure of this? When is this stuff actually being executed, right? Because they don't think about it, they don't understand the impact that it has on the performance of the event loop. Okay, so this is critical. The key thing about both of these, next tick in queue microtask, is all they do is defer execution to the end of the current stack. Okay, so let's say I'm running a bit of JavaScript. Okay, so I have one line, 2 lines, and then I call next tick, and I give it a function, right? Then I have a few more lines of JavaScript. Okay, and then after this JavaScript runs, control is going to return back to the C++ layer. Okay. All this next tick is doing is saying that function that I'm passing to it is going to run at the end. Right. All that's all it does is just defer the execution of that function. Next, or queue microtask, exact same thing. Right. The difference here is queue microtask is a standard that you'll find in browsers as well. It's attached to promises. Uses the same mechanisms as promises, but it also will just stick a function to the end. Okay. And then the thing to keep in mind is next ticks will happen first and then queue microtask. Okay. That's all you're doing. Okay. This will come into play in a few minutes when we talk about event emitters and streams and how we achieve asynchronous activity in streams and event emitters. So just keep that in mind. Next tick just is deferring it till later. The other scheduling mechanisms we have, of course, are timers. So set timeout, set interval. We have what are called immediates. They're kind of looped with timers, right? They're kind of combined with timers and stuff, but they're not. A set immediate, it basically just registers a callback that will turn at the end of the current event loop turn, right? So like I said, every time the event loop turns, there's a series of tasks that it completes. Immediates are the very last one before it iterates back. Now, if you look at the documentation, a lot of folks will say, oh, the set immediate start, is it the start of the next iteration? Well, it's just because that's what it appears to be, right? It's kind of a semantic thing. If you look at the actual code and everything, it comes at the very end, but it's right before it turns and does the next thing. So it doesn't really matter. But set immediate and next tick, the names of those really should be inverted, right? Set immediate is not immediate. It's at the next tick. The next tick is immediate, not at the next tick. So I blame all the Node contributors that came before me. That's a long-standing thing that we haven't been able to get to. So there are other ways of scheduling things. Of course, we have promises, right? But promises by themselves don't give you that parallelism, right? We'll talk about that in a bit. You have to actually make sure that the promise is scheduling something to run asynchronous. We do have callbacks at the native layer. This is not necessarily something that's available to JavaScript developers, but at the native layer, we have ways of setting a callback and actually deferring it to the libuv queue so that it is invoked at some other point in the event loop. We'll talk about that. And then, of course, we have worker threads. which if we have time, we'll go into, but basically a worker thread is its own node instance. It has its own its own event loop. It's running in its own thread. It has its own copy of the node standard library. I mean, it's basically a complete node instance just running in a separate thread. But it also allows us to defer activity. It works because it's a separate event loop, right? It does, and because it is its own separate event loop, it actually has its own V8 isolate, which is what we use to run the JavaScript code. So it can run JavaScript in parallel with what's happening on the main thread. Okay, but it's best to view it as just a separate node instance running in the same process. Okay, all of these scheduling mechanisms kind of work together, and it's important to understand how they come together. But if you understand how next ticks and queue microtask work, the rest kind of really fall into place. Okay, keep moving. Any questions on that bit there before I start going into Event Emitter and kind of how this starts to come out? Common expensive synchronous code. So the question in the chat, common expensive synchronous code that I've seen, JavaScript or not JavaScript, JSON parsing. Had one customer that they were parsing. They had one JSON document that was 10 megs that they were parsing in all into memory. But that's not all, right? They were doing something with this data, and this is the scary part. What they would do is synchronously start to iterate over every field in that JSON document. Okay. For every field, they created a promise that would go off and do some processing for that for that field. Now they would go deep. It was recursive into the structure. Okay. Every single one of those promises might change the document in place. Okay, so they're creating this massive JSON document, creating promises for every field in it, modifying the JSON document, and kind of it's not a document at that point. This massive object structure in place, and would then resolve that down and wait for all those promises so they can have the modified document that they would then serialize and send out to the client. Okay, they weren't using any caching at all in this, right? So one of their requests actually in this particular case blocked the event loop by a full minute. Okay, like typically when we're talking about event loop blocks, we're talking about orders of milliseconds, right? This stopped the event loop for a full minute while it was processing this document. A lot of those promises were synchronously resolved. So they would just use like promise.resolve or new promise was purely synchronous code and a bunch of .then chains in there where it would just all be synchronous logic. I have another talk called Broken Promises. If you search for it on YouTube or whatever, I've given it a couple of times, and I did a couple of workshops with my colleague Matteo Kalina on this, where we go into a lot of those details, where people get promises wrong. I highly recommend that. I mean, that's a whole training we can do just on that. But yeah, that's probably the most egregious one I've ever seen. The question, isn't promise resolve executed in the next tick of the loop? Promise.resolve. That promise will be resolved, directly, right, immediately. Okay. If there's no then attached to it, then all it is you're allocating a promise and not doing anything with it. If you put a .then, that is the same as calling queue microtask. It is scheduling that continuation, that function on the then in the microtask queue, so that the next time control returns back to the C++ layer, that's going to get executed. Okay. Make sense? Okay. So let's talk about Event Emitter. What is an Event Emitter? It's one of the things it's one of the APIs that have been around the longest. Pretty much everything in Node is Event Emitter. It's, if you see an object that has the on, right, where you give it an event name, and then you pass it a function, right, or once, event name, function, and then you have emit, event, and some set of arguments. Okay. So like the process object, streams, like I said, pretty much everything. You throw a rock at it in Node, it's probably an event emitter. This is it's this is the first bit of code that's executed in JavaScript or in Node, for instance. We have to load it. It's because everything becomes it. So what is happening here, and how does it work? All right. So inside the event emitter object, right, we have a table, and this is it's just an object that has keys and values. Now the key names are the event. Right, the event name, and the value is an array. Okay. Anytime you call on, all it does is take that function and add it to the array for that name. That's all it does. Okay. And keeps it there. All right. Once we'll take that function, wrap it inside another function, and add that to that table. Now that wrapper function, what it does is when it's executed, its only other task is to remove it from the array. So the first, as soon as that function is executed, it just pulls it right back out. Okay, that's all on and once do is just add those functions to those tables. Okay, now emit, what it does is it will go out and grab that array. Right, it'll make a copy of it in case it's modified in process. And then it will just iterate through just a synchronous for loop for each of these functions in this array, execute it one after the other. Now, it's important to understand emit is always synchronous. Always. Okay. It will block. It will call those functions in the order that they were registered. It does 1, 2, 3. If the first one takes a long time, if the first one errors, the other ones will never be invoked. Okay, it is just and once or emit will not return until all of those functions have been called. It is always synchronous. Okay. Now there are tricks though, right? That we use in Node. I mean, if you're familiar with Node at all, you know that wait, some of these events seem to emit asynchronously, right? They don't appear to happen synchronously. The functions themselves are actually invoked. What we do internally are use things like next tick to make it appear that it's asynchronous, right? So the functions themselves, the handler functions that we pass in, right? Those are executed synchronously, but those handler functions, what they might be doing is saying, okay, next tick this or defer this to some other point. Okay. This is critical because, like I said, everything in Node is event emitters. Node streams are event emitter, right? Node streams by themselves are not asynchronous. Every function in a Node stream executes synchronously, right? And will block the full time it's running. But we use tricks like next tick to provide this asynchronous behavior. Okay. And we'll see how that how we do that in just a bit. But event emitter, this is critical. I mean, it's a super simple object, right? Maintains a table of functions, runs those functions. Okay. All right. So let's talk about streams. Let's see how we're doing on time. Okay, we've got plenty of time. Good. All right. So let's talk about streams. And this is going to be specifically node streams. All right, we'll talk about the web streams in just a bit. When I say web streams, like I said, I'm talking about the same API that you'd find in the browser. With node streams, you have objects readable, writable, duplex. I'm going to apologize now for my handwriting. I know it sucks. And transform. Okay. Now, readable, it's an event emitter. I'm just going to say, I'm going to abbreviate EE so I don't torture you guys with that too much writing. Writable, again, it's an event emitter. Duplex, because there's no multiple inheritance in JavaScript, we have to, we have some tricks for how we do this. but duplex implements both the readable and writable APIs. Okay, so it is, yeah, again, also an event emitter. And transform is just a specialization of duplex. Okay. Now, readable, I mean, just, it probably, maybe obviously just going to kind of cover all the bases. Readable is, you're reading streaming data coming in. Writable is where we're passing it out. All right. So let's focus on readable first. The readable streams that we have here, what it's going to maintain is it has what's called a high watermark and a queue. I'm greatly oversimplifying this, so just to give you the basic concept. High watermark specifies how much data can be in the queue. Okay, so we don't just constantly eat up memory just by pushing too much in. The thing that's important to understand about the readable stream implementation, though, is that it does not enforce the high watermark. It will allow an implementation. Yeah, the queue would be the buffer. The implementation gives you the feedback, right? And we call that back pressure. It says, hey, my buffer is full, right? But it won't stop you from still filling it up. You can keep pushing data into that. There's a function called push. It's considered an internal API, but it's on a stream. What push does is it takes a chunk of data, pushes it into the queue. Okay, it returns a Boolean. If it returns true, then yes, you can push more. If it returns false, the queue is full and you're not supposed to push more. Okay, but you can. All right, and it will keep accepting whatever you push into it. All that's going to do is drive your memory usage higher. Okay, now when data has been pushed into the queue, the internal of the readable stream will emit a couple of events. One is readable, right? And basically what that event is telling you is this stream is readable. It has data. Okay. And if you get the readable, if you're listening for the readable event, there is a read method that you call. Okay. This is readable. So it's telling you, okay, now call read. When you call read, you'll get a chunk of data out of the queue, right? You keep calling read until there's no more, until it says there's no more data in the queue. Okay. That's the pull model. One of the most complex things with node streams is there's actually 3 different versions of streams in one implementation. There's a pull model, which is here calling read. There's a push model, and then there's a hybrid push and pull. It's lots of fun. But if you're listening for the unreadable event, then it's not going to give you the data. You have to pull it out using read. Okay. There is the read event. Okay. If you're listening to the onRead event, what onRead will give you is it will actually give you the data. Right. So instead of waiting for you to pull it out, right, it will just say, okay, data is available, here it is. And it will keep firing that event over and over and over again, as long as there's data available in the queue. Right. Now it'll do so synchronously. So it'll call read, more data. Okay, read, more data, read, more data. It will drain the queue until all that data is out. So it's up to you to, if you need that to be asynchronous in some way, yes, it does remove the data from the queue when it does read. I'm just seeing if you're not following along in the chat, questions are being dropped in there. So it will sit there and just pump that data out, right? Now, as long as if you have an active read listener, right, and every push will just immediately go out to read, right? It won't go into the queue. It only goes into the queue if there's nobody actually reading, right? So if you have a read event handler there, it's just going to flow right out. And we actually call that the flowing mode for the stream. Okay. Now, all of this is based on the event emitter model. Okay, so you use onRead to add, right? To add your event listener. The stream actually, it is an event emitter instance, so it has its table of event handlers in here. Okay. Push happens, it comes in. Do I have a read listener? If so, just push it out, push the data out. If I don't have a read listener, if I'm not in that flowing mode, queue it, right? If in that case, it's going to say I'm going to go emit readable, right? Because there's data available now. Now, while you're waiting to respond to that, you may, something else might still be pushing data in, all right? So you have to, just depending on how you defer the readable handler, you might push that till later. There might be quite a bit of data still that gets accumulated in that queue, so you have to watch that. The read is the one, the read handler is the model that you most typically see with most node streams code. You'll see with the read events, you'll see the end events, which is like, okay, there's no more data to read. You'll see the close event, right, which is, okay, this thing is closed off and we're done. Or we'll see the error event. All right, there was an error processing this somewhere, you need to handle it. Okay. Again, all of this is happening synchronously, right? Just like the event emitter, the readable stream object has nothing built into it that is async, that calls any of the scheduling mechanisms at all. It operates purely synchronously. So where you get the asynchronous aspect of streams is by deferring when you call these different things, right? So when do you call read, right? Or when is push called, right? When you are creating a readable stream, let's say if you're producing one of these things, you have to give it a read function. Okay. Now this read function, the stream will call it repeatedly as long as its buffer is not full. Okay. So it will keep calling it until that buffer is full, right? But it will wait. When it calls once, it will wait until you call push before it'll call again. Okay. So it's asking you, give me some data. That's what this read function does. When you create the readable and you give it a read, it's saying, give me some data. And the stream will wait until you give it data. If you call push synchronously right away in read, if the buffer is not full, it will just call read again. Give me more data. Okay. Up until you say push null. Push null is the signal that I'm done giving you data. We've reached the end of the stream. Okay. So you can provide all of this synchronously. Like the first time read is called, you can give it all the data just by pushing, push, and then push null. And the entire stream will operate in a purely synchronous model. Okay. Or you can defer these push calls to some other point in time. Maybe you need to do some file IO. Maybe you're reading some file and you have to wait till that callback is invoked, and then you would call push. Okay, it's up to you to provide that asynchronous aspect of it and the scheduling of it. You don't get any of that for free. Okay. That makes sense? Okay. So there are some other aspects. I mean, there's ways of erroring the stream. I'm boiling it down to kind of the most simplistic basics here, just to give you an idea of how these things are working under the covers. Push, this read and push, if you're providing the stream, those are your critical APIs. And if you're consuming the stream, your event emitter, readable, read, close, end, error events. Right? And if you are using readable, then the read function there. Okay. Okay. So that's the readable. The writable is very similar. when a writable is created, you have to give it a write function. This is kind of the internal write function, and it's going to get a chunk, an encoding, and a callback. Okay. On this writable stream, I'm going to prefix that with an underscore because it's the internal function. I'll get to this question in just one second. And then there's an external write function where you just give it a chunk. Okay. When you call that, right, it will just call your internal function to write it. Okay. This internal function has to call the callback, right? So the stream, what will happen is that, let's say you write 10 chunks. If the first chunk that is written, if that internal write function does not invoke callback, right, what will happen is that the chunks will accumulate in the writable's internal buffer. Okay, and then when callback is invoked, it will grab the next chunk, write it. Okay, and then it'll drain that way. So if write is calling callback synchronously, then all of those writes will happen synchronously. If it is deferring invoking that callback, then all those writes will happen asynchronously, but the data will accumulate in the internal buffer up until the high watermark is hit, right? Well, actually beyond, it'll tell you my watermark, my buffer's full, but you can keep writing to it. You should not, but you can, right? And there are events there, like there's a drain event in there that basically tells you my buffer is not full anymore. You can keep going. There are other API, some other APIs in here. One is allows you to block it. Again, my mind is, the name of the function just completely just escaped my brain just now. You can basically cork it. You cork the writable stream so that it will defer everything you write to it directly to the buffer, rather than having it go straight to the write function. And then while it's corked, it will just accumulate. And as soon as you call uncork, it takes everything that was in the queue and just dumps it into the write function. Okay. So there's ways of kind of, controlling the flow of data that goes through. But when it comes, the simplest way of looking at it is you have this external write API, and all it does is defer to the internal write function to output the data with some buffering in the middle. Okay. Now this one, if we register two functions as readable callback, it will be the case that the first callback will steal the data from the second one. It depends. So the readable event does not give you any data. When you get the readable event, you have to call read to get that data, right? When you call read, it does pull the data out of the queue. So what ends up happening is the first one of those event handlers to call read is the one that gets the data, right? If you register the read event, though, every handler will get a copy of the data, right? So it's taken out, and it's actually not a copy of the data. It's the same reference to the same data. So it'll get a chunk and call this function with this data. And so if one of those handlers modifies it somehow, all the other ones will get the modified data. Okay. Generally, good idea. Try to only have one read event handler in a stream, only one readable. And there's methods there where you can check to see if there's already one there. Okay. But there are valid use cases for setting up that kind of pipeline where you actually want them to modify or consume the data in different ways. It's very difficult to get right, so be very deliberate about it. To trigger the writable callback, use something like write null. Write null will end the stream. It's essentially how you would close. It's one of the ways too. And there is also an end there. And so the callback is internally triggered. It has to do with the where the buffer is, right? If it's not corked, if a stream is a writable is always writable unless it's been ended, right? But if the queue fills, then you're going to get some events like drain and stuff like that, depending on kind of whether it wants you to write or not. If that makes sense. So those all of the events other than error and close, all of the other events are largely kind of advisory for writable stream. Close is I'm going to error the next time you try to write something to me, and error is just like terminal. This thing is no longer usable. Makes sense. Okay, so a duplex. All right, so great on time. Like I said, a duplex implements both readable and writable, right? And it's best to view them as being separate. Because in the duplex implementation, those are not connected to each other, right? It's just you have both kinds of objects in one. All right. The buffers, they have their own buffers, right? Yes, it's all events. Like if you get a close event, it's saying that both sides are closed. If you get an error event, it's saying both sides are closed. But they'll also still emit the events specific to each individual type. So you'll get a read event, right? Or you might get a drain event, right? It really mashes the two up together, but they are distinct streams. You can write one to one side and it has absolutely nothing to do with the reading of the other side, right? It's not that you write to one and then read from and get that data when you read. We use this for things like sockets, right? Where the writable side is the outbound channel on the socket, and the readable is the data you're receiving on the socket. Okay, pipes and all that kind of stuff is the same way. Okay. Again, there's no connection here, but you have to look at them as these are essentially two separate objects, just mashed into one. With a transform, however, it's different. A transform is a duplex. Okay, we have the writable side and the readable side. And again, these still have two separate queues. All right. But what happens is when you write something to the writable side, like I said, there's this internal write function in a writable. Okay. What ends up happening in a transform is that the implementation of that write will pass that chunk through a transform function. Okay. That will potentially modify the data. And then it calls push to pass it into the readable side. Okay. So you write something, it goes to internal write transforms, transform pushes back in. Okay. So with a transform, the readable and writable side are always connected through that flow. Okay. Now, again, that happens completely synchronously. Right. It's up to you in the callbacks, right? And then the event handlers or those kinds of things to add the asynchronous bits. Okay. Important to understand, like I said, these still have two separate queues. The writable side and the readable side will still have their own high water marks. All right. The type of data, especially on a transform, the type of data that you write in, probably not the same kind of data that you get out. All right. So if you think of like a texting, like a stream that's doing text encoding, right? You might write in a string, get out a typed array, right? That kind of thing. They're still operating, these two sides, this readable and writable side are still operating independently. They're just connected through this transform. Okay. That's the quick down and dirty version of node streams. Any questions on it? Hopefully that's useful. Okay. explain how the piping. Yeah, good. Okay, so piping. Say we have a readable. Let's say we have a transform, which is a writable and a readable. And then we have a writable. Okay, we're going to set up a pipeline. What ends up happening here is when we either call the pipe function or we use the pipeline API, it's actually fairly complicated what all it does. But essentially what it's doing is setting up all of the event emitter, all the event handlers, for it to actually flow the data through. So what will happen is that we will add a read event handler on this readable. Okay, that when the read event happens, it writes to that writable. Okay. Now, but if this is the transform in place here, of course, that's going to pass it to the transform function, right, to the readable. And then if we want to pipe here, we're going to do the exact same thing. We're going to set a read handler that will take that will get the data from here and write it to there. That's all the pipeline does. Is it just sets up the events so that the data will flow all the way through. Now it sets other events, like it will monitor if one of these closes, it will close all of them, right? If one of them errors, it will error the entire pipeline, right? If the write on any one of these returns back pressure and says, my buffer is full, then the back pressure will be propagated all the way back, right? So those read and write functions are intelligent enough to know, okay, where I'm sending this data to, it's full. I'm going to pause reading for now, right? And while it pauses reading, the stream in the back can still be pumping data into its buffer, right? So it might still be accumulating. So what you want to try to do is communicate that back pressure all the way back as far as you can and tell whatever the source of data is that, hold on, I need you to wait, right? And we have the node APIs for like reading a file, right? That stream on the file read stream. It will respond to that. If you tell it to pause, it will stop reading data from the file system. Right. So it won't constantly accumulate, but the pipeline sets all of that up for you. Okay. Now you can create, and this is one of the unique things with node streams, you can, so the same objects can participate in multiple pipelines, right? So you can create a file and, and it's reading data once, because it's using the read function. Like I said, every time the read handler is called, it gets the same data, right? You can actually set up multiple pipelines where that data is just flowing through. And it ends up being very, very efficient. But again, the entire thing can be set up completely synchronously. Pipeline and pipe in Node, we make use of next ticks in there. So we add a degree of asynchronous processing, so that it's not always forced to be synchronous, and we're allowing the event loop to turn as we go. Okay. Okay. So how does this differ from web streams? So we added the readable stream API last year. It's still new, still experimental in there, but you also have like the writable stream and then transform. Okay, so how do these differ? The key difference is that what we call web streams are all promise-based, entirely promise-based. So node streams are event emitter based. Okay. Web streams are all promise-based. Okay. Inside, so let's say a readable. I'm gonna abbreviate this. Readable stream. Okay. You get what's called a reader, right? And every readable stream can only have one reader, right? It locks it to that reader. And once you have the reader, right, no one else can consume that stream. So that's one of the key differences from node streams. Like I said, with node streams, you're going to set up multiple pipelines. You can have multiple, listeners on those events, right? And any one of those listeners will get a copy of the data. With web streams, there's only one consumer at a time. Okay, so you get that reader. Okay, what is bundling under here? And that reader has a read function. Okay, that read function returns a promise. Okay, inside that readable stream, when it was created, we have what's called a controller. All right, if you're familiar with the new readable stream, it's the first object that you pass into that constructor. It's this controller object that you have to push the data in. The controller has this enqueue function. Okay, your code, the callbacks that you pass in when you create a readable stream is going to use the controller to call back and push data in. And queue is the function that's actually used to push. So it is the equivalent of NodeStream's push function. Okay. What ends up happening here is when you call read, it's going to go in to the controller and say, is there data in the queue? If there's no data in the queue, it's going to go off and call your function for pulling data into it. Your function runs, calls enqueue to push data in. Okay. When your function pushes data in, it's going to go off and resolve that read promise. Okay. With the data that you just pushed in. If there is data in the queue, then when you call read, it's just going to pull that data out of the queue and resolve that function immediately. Okay. It's not going to go off and call this function to enqueue. It's just going to try to read it from the queue, the buffer as it is. If you are reading and because that function that calls enqueue, it itself can be an async function, so it can return a promise. If it calls once and that promise has not resolved yet, and somebody comes out and keeps calling read, what's going to happen is that those read promises are going to accumulate into a read queue. Okay, so we have a data queue and a read queue. Okay, and then as data is actually pushed into the read to the data queue, it will check, do I have a pending read? If so, I'm going to fulfill that promise with that data, right? And then they'll try to balance each other out. You will not accumulate reads if the queue has data. Okay, you'll only accumulate reads if there's no data in the queue yet, right? And we haven't signaled that we're done. You'll only accumulate data if there are no reads. Okay, but it uses promises back and forth. It's just a chain of JavaScript promises for fulfilling all this. Okay, so we either resolve the promise immediately or we queue it. Okay, that makes sense. There's no events in here. It's all promise based. Right? That is the key difference here between the two. Now, in node streams, like I said, by default, node streams work entirely synchronously. Web streams operate entirely asynchronously because the continuations are always deferred to the microtask queue. Right? You read something, you write something. Every operation, even if you on the constructor, you have this start function that you pass in. Even if you do not define that start function as async function, it's run as an async function. The pull event or the pull, there's actually a pull method that you pass in. This is the thing that actually prompts you to call enqueue. Even if that's not an async function, it's run as an async function. We create a promise on the back end if the function doesn't return one. All right, and the continuation always is forced to the microtask queue. Okay, now it it works. It's a good model. It works in the browsers. I mean, you can write the same web streams code that works in browsers and Node and Cloudflare workers. I mean, it's all there. The problem is that it's a whole hell of a lot slower than Node streams. What we're seeing is that the performance of web streams is several orders of magnitude slower than Node streams because of the way that it's orchestrating these promises and the continuations. Okay, so if you're wondering Node stream or web stream, it has to come back. What performance do I need? If you need something that is high performant and it doesn't need to be portable, right? You can only run a node, use node streams. If you need it to be portable, right? It's working in multiple environments, and then you want to use web streams, but you're going to be sacrificing performance. Okay. Now, the way piping works with web streams is different. Again, it's all promise based. We have a readable stream actually has this pipe to and pipe through. Okay. Again, with node streams, you're setting up a sequence of event handlers. With pipe to and pipe through, you're basically just setting up read promises followed by write promises. Right? So it's essentially get a reader, read, await the read. When that resolves, await write. When that resolves, you go back and do it again, right? Until the stream signals that it's done. So all that pipe to is just a long, and it can end up being a long sequence of promise continuations. Okay. Again, it can be much slower. Now, in certain runtimes like workers, for the internal streams that we have, so when you have a readable stream that you get from inside the runtime, there's various optimizations that we can apply. We haven't implemented those optimizations in Node yet, so that's still going to be fairly slow. But in the future, one of the things that we're going to be doing is optimizing those and finding ways of making those a lot faster. Are web streams generator based? No. If you're not familiar with the generators, it's where you have a function, and then you have like the asterisk, and then you can have the name, right? Generator function supports the yield here. Every time you call it, it's going to maintain the state and just yield the next value from that. Web streams are not generator based. They support generators. You can use generators with them, but that's not what they're based on. Okay. Both Node and web streams support async iterators, so you can use for await, like const chunk of, right? You can use that for await syntax for both kind. Let's talk, let's switch directions a little bit. Let's talk about traditional callbacks in Node, kind of how that works, and go back to libuv and kind of give you some understanding here. So like I said, we have this JavaScript layer. This is where your code is running. Okay. And let's say you want to read part of a file. So we're just going to read some chunk of a file. Okay. That read function, you're going to give it some parameters, have some args and a callback that you give it. Okay. What is happening inside Node? Okay. First, we cross what's called the C++ boundary. Okay. And what we're doing in here is we're calling into an API inside Node defined in this Node file CC, right? So this is C++ code that we're calling into. Inside this file, there is a read function. Okay. And it is going to schedule the file read on the libuv thread pool. Okay. So there's actually, I can't remember the exact name of it, but there's this UV API for like reading. Okay. We pass the arguments in, okay, after they're translated to C++ equivalents. We pass those into this libuv API. this libuv API is given what's called a handle. Okay, it's a struct defined by libuv that records the context. Okay, and what I mean by context is it primarily keeps track of this callback. Okay, it is what are we going to do after we read. Okay, that's kind of the critical thing. I'm oversimplifying it, but this context, this handle, is the thing that records. Yes, I'm starting something that's going to happen in a different thread, but when that comes back, what am I supposed to do next? Okay. That API will defer out to libuv's thread pool. So one of these 4 threads that's happening out there will pick up that task to read that file, and then it will come back to the event loop and say, "This is done. I read this chunk of file." The event loop is turning. It comes back to where it's going to check IO. Is there pending IO, or is this done? And when it does, it's going to say, "Okay, great. What do I do with it?" Okay. And to answer that, what do I do with it, is it looks up this handle, right? Checks to see what context is associated with it, and then invokes it. Okay. So in this case, we're seeing that, okay, there's a JavaScript function that's attached to this. We're going to go invoke some JavaScript. Okay. That is the pattern for everything, all of Node's built-in APIs that accept these callbacks like this, and it says that this is asynchronous. That is exactly what is happening, okay, in every single case. Okay, it's going to go down, defer to the event loop, execute it, or not the event loop, the thread pool, execute it there, and come back. Okay, file system, network stuff, DNS. If you use the web crypto API, all right, like all that is promise based, but under the covers, it's using the same thread pool. Now, there are a default of only 4 libuv worker threads per process. If your application is doing a whole lot of file IO and DNS lookups and crypto, right, that means there's a lot of activity that's contending for just 4 worker threads, right? Always a good idea to do some profiling with this, but there is a command line option for increasing that default, right? So you actually want to make sure you're tuning the size of your thread pool to the amount of asynchronous tasks you are scheduling on it, right? Now, here's the thing that a lot of people don't realize with worker threads. Like I said earlier, worker threads are essentially their own full node instance, right? So you have the main thread, which is the one that started when Node starts, and it has its own event loop. And you have a worker, and it has its own event loop, and it's executing JavaScript in parallel, and everything's looking great. Okay. What you have to remember is they all share the same 4 libuv worker threads. Okay. So if your main thread is scheduling file IO and your worker thread is scheduling file IO, those are going to contend with each other. Right. So, we run into problems. A lot of people will think that, okay, I'm just going to defer stuff off to off to a worker and everything's great. But when the workers and the main thread, they're all doing asynchronous IO, and then we have, they run into a lot of performance issues and things. They don't get the results that they actually want. Okay. So either you need to increase the size of this pool to handle that, or you limit your IO to just your main thread and use your worker only for compute. So anything that is synchronous compute. So you think like encryption or parsing stuff, or creating 30,000 promises or in loops and that kind of thing, right? You defer that. And what ends up happening if you do this right is you free up your main thread event loop to handle all of the IO, and you can have a whole pool of worker threads that are handling the more compute intensive things that would normally block your event loop from turning. Okay. There's a library that I created with Anna Henningsen when I was at Nearform called Piscina that implements a thread pool for worker threads. Highly recommend you taking a look if you're going to do any kind of work with worker threads. I'm waiting for him to actually publish this, but Matteo Kalina has a project where they made use of Piscina and Fastify and a bunch of the modules that that they've created, and ended up with several orders of magnitude performance improvements on for customer stuff. I'm waiting for him to write this up. I think I'm overdue to ping him again to ask him when it's actually going to come. But watch for that. It will be published out on the Nearform weblog when it comes. So hopefully within a couple of weeks time, but it's going to be invaluable. There is another. I'll have to send Tracy. I'll have to send you the link later on because I can't remember exactly where it is now. Another customer I worked with before ADP, they did a whole study on performance improvements that they were making, all around promises and abuse of promise.all. That is also extremely valuable for digging into a lot of this stuff. Okay. I don't know if we have time to go into too much other stuff. So there's a couple of tools that I want to point out. Clinic.js. It's a open source performance analysis tool. It was created originally by Nearform. While I was there, I mean, I've been with Nearform for about 9 months now, but we created it while we were there. It's all open source, free to use. Anybody can make use of this stuff. In fact, let me, I can actually pull this up. Let me stop sharing this. Get over. What it does is it will go out and start to analyze your Node application and help you detect what kind of problem you're having with it. Yeah, if I can find the right screen there. Here we go. All right. So I'll get to exactly why I'm, pointing it. There's one very specific thing I want to point out, but I want to give you the overview first. So Clinic Doctor is one of the tools in there. If you run it like on a 10-30 second sample of your code, right? So if you have a Node server, for instance, and you throw a little bit of load at it, right? What Doctor will do is it will look at your event loop. It'll look at your memory. It'll look at various heuristics that it's in how it's running, and will attempt to diagnose the kind of problem you're having. So you're like, okay, my performance is slow. Why? Well, Doctor will come up and tell you, well, you're blocking your event loop for too long, or you're stressing out your garbage collector too much. And then here's what to do next to look at that. Okay, so it answers the question, where do I start, right, in diagnosing performance issues. Flame gives you a CPU profile of where your code is spending the most time. And unlike like if you use Flame graphs in Linux and Perf and some of those tools, which only give you kind of that system level, that C++ level, Clinic Flame actually digs into the JavaScript also, and it will tell you both at the system level and in your JavaScript where the application is spending the most time. So it tells you where your synchronous blocks are. If you're blocking the event loop too much, Flame will tell you exactly where you're blocking the event loop, and that gives you the right place to go look. Heap Profiler does the same thing, but with memory allocations. If your application has a memory leak, the Heap Profiler Flame graph will tell you exactly where that memory is being allocated. Extremely valuable. Bubble Prop is the one that I wanted to show, though. It's really, it takes a lot of getting used to kind of figure out how it works. But Bubble Prop will visualize the asynchronous flow of your application in aggregate. So it will tell you where am I branching all my promises, right? Am I spending too much time scheduling code than I am running code? which seems to be a big problem. People will unnecessarily schedule asynchronous activity when just doing it synchronous is more effective, right? It will break it down how much, if I have a server, a web server application, you want your application to be spending more time actually processing the HTTP request than resolving promises. Okay. But if you look at BubbleProp and look over on the side, you see there's this little chart thing over on the side. If you look at that, it will tell you basically what percentage of time your application is spending doing what. And I've seen cases where it was a web server, but the networking processing was only this tiny thin, like one little pixel line at the top. And then everything else was this purple, which is scheduling, right? And what's that telling me? It's saying I'm using promises way too much, right? Or I'm using next tick way too much, right? And as soon as you see that, I mean, you can ignore the rest of the chart. If you see too much scheduling over there, you know I have to go refactor my Node application to eliminate some of these promises, because that means your application is doing nothing but, okay, I'm going to schedule this for later, and then I'm going to schedule this for later. I'm going to schedule this for later. And it's spending so much time thrashing around the scheduling that it can't get to what you want your application to actually do, which is serve requests. Okay. Using tools like this, I mean, so having this basic understanding, of how these things work, right? But using a tool like this will really give you insight into what your specific application is doing. And I point this out, to anytime I do any kind of node performance, any talk, or helping people out, I always point them at this tool and say, tell me what your application is doing. This is always my first step. So I can't let any advanced node talk go without talking about this at all. So we have about just over 10 minutes left. I've gone through everything that I had planned for. So let's open up to any additional questions, clarifications, things that folks might have.
Yeah, thanks, James.
I have one sort of generic scenario that I wanted to ask you about. If you're in a browser setting, and I've had this situation many times where I've got to pull in file data and then immediately turn around and write it back out or up to a server, do you reach for pipes or duplex? Like I feel like I've done it every different way and never very optimally.
Right. So the first caveat I'll say is Node is horrible at static file serving. Right. It is not designed to serve static files. If you look at how Nginx works and all, the ones that are actually designed for this kind of stuff, they're not pulling chunks of data one chunk at a time up into JavaScript and sending them out. They're using like a send file system call and sending it out directly. The way that you want to do it, if you are going to do it with Node, is you're going to create create read stream, right? So fs.create read stream, right? And pipe that directly out to the response. So whatever response object you have, you're just going to pipe, and you'll use the pipeline API. Don't use the .pipe, right? Because that only sets up one part of it. You want to use the pipeline API that's directly on the stream module, and that will set up the entire structure. Now you'll have to do error handling around that, and there's additional work you need to do, but that's the one you want to use, right? There's not a way to make that faster. The HTTP2 API does have a respond with file method, which keeps you from having a pull chunk by chunk of data into JavaScript land. It does all of the data transfer at the C++ native level, and it's order of magnitude faster. But HTTP2 and Node is kind of buggy and problematic right now. There's reasons why you not want to use it. If it's a big if I can get around to it later this year and keep working on HTTP3, those mechanisms will be there as well, so where you can do all this data transfer much more efficiently without pulling it. But for now, HTTP1, you want the pipeline function and create read stream.
Awesome, thanks.
There was another question in the chat for you, James.
Oh, okay. Let's see. How does async we interact with the microtask queue? Okay, this is a good question. Let me see if I can switch back over here to remarkable. Okay, so a async await is just syntactic sugar for a promise. Okay, so what happens if you have an async function? Okay, it's going to have some bit of code, right? You might have an await something. Okay, and then you're going to have some more code, right? So what's happening here? This is just a syntactic sugar for saying something like new promise, right? And then in this promise, you're going to run that code. Okay. And then something. And then the last bit of code. That makes sense? The first line of code in that async function runs synchronously. As soon as that async function is called, it's going to start executing that JavaScript right up until it hits the first await. Okay. When it hits that first await, that's essentially you're scheduling a promise, right? It's going to go off and do that thing, right? And then everything after the await is equivalent of running in a then. Okay. So everything before the await runs now. Everything after the await is deferred to the microtask queue. Make sense? Always. So there is some complexities and stuff in here. You have to be careful. For instance, in an async function, if it throws an error, right? All of the memory that's allocated, that's in that closure, in that function closure, is going to be held and not garbage collected until you read the stack property on that error, or until that error is garbage collected. So, it can be held for a long time. If you have a really complex async function, like imagine if you have an async function that's allocating a 1 meg buffer, right? Or, whatever, that's going to be held, all right? It's not going to be freed. That function could be long gone, but you're keeping the error around, right? For some reason or whatever, you're propagating it through. All of that memory is, and all the memory it's attached to. So this is the closure around a larger bit of stuff. It's going to hold on to all that memory also, right up until the stack method is read. But yeah, and so that's basically how this works. I mean, it's very simple here. Just before the await runs now, after the await is deferred. Okay. Let's see. Any other questions? Let's see. Okay, we have. Can we use client profile our serverless functions too? It depends where those are running. So like with Lambda, probably not. Like if you could run the code locally, right, then it'll work, right? So like Azure functions have mechanisms where you can run them locally. So if you're using those, yes. With Cloudflare Workers, right? If you're using Miniflare, you can use it there because that's running a node. If you're using AWS, right, it's going to be a pain in the butt, right? Using Lambda to do it. So unfortunately, it's not as great there. Let's see here. Any resources to visually cover the life cycle we covered today? Yes, there's. With this, I would just point to some of the talks that Matteo and I have done over the past few years. I mean, we can get the links out for some of those. The broken promises talk is one I definitely highly recommend. Some of it's a bit dated. I mean, it was like, I think 4 years ago that I first gave that talk. But it still provides a lot of really good information. I think, yeah, thanks. I'm gonna drop the link in there. Let's see, the next question. You've said several times we can easily think we're running already async code that's actually getting executed synchronously. Yep. Easy clues that we're doing things the wrong way is look at your event loop block. Look at your event loop delay. Clinic Doctor will tell you what it is. There's another metric in there called event loop utilization. It's relatively new. This tells you how efficiently you're using your event loop. Right? It's really, it takes a lot to get your head around, right? But there is a threshold at which you're either overtaxing your event loop or underutilizing it, and event loop utilization will give you that. And it's oftentimes where you can actually throw more stuff. You know, your event loop is going, your delay is going up, but that might be okay because you're actually using the event loop efficiently and effectively for the type of application that you're running. Right. So it takes quite a bit of intuition to get going, and more than we can talk about in an hour and a half here to go through. So that would have to be a separate thing to go through. Okay.
Cool. Oh my gosh, so much. I feel like a lot of us feel like we have to watch it like 3 or 4 or 5 more times. And, you know, maybe you should just turn this entire talk into a book like that. That would be helpful. In your free time, of course. In your free time. Thank you so much, everyone. Just make sure to follow James on Twitter. He's amazing. He's just such a great community member in Node, and we just love you so much. And you can follow him at James Snell on Twitter. Yeah, thanks everyone for joining, and we'll see you soon.